Markov chains moved in discrete ticks, one step, then the next. But radioactive decay, customer arrivals, server requests, they don't wait for a clock. They just happen, whenever they happen. The Poisson process is the continuous time model for exactly that, a count of random events that only ever increases, one at a time, at some constant average rate. A Poisson process n of t counts events up to time t. It starts at 0, and the number of events in disjoint time intervals are independent. What happened in one window says nothing about another. Its increments are stationary. The distribution of how many events land in an interval depends only on the interval's length, not on where it starts. Put those together with a constant rate lambda, and the count in any interval of length t is Poisson distributed, with mean lambda t. That's the defining result. Equivalently, the waiting time between consecutive events is exponential with rate lambda, and successive waiting times are independent and identically distributed. The exponential is memoryless. However long you've already waited for the next event, the remaining wait has exactly the same distribution. The process has no memory of the past. That's the continuous time echo of the Markov property. The future depends on the present, not on how long you've already been in this state. Watch a sample path. N of t is a step function, jumping up by 1 at each random arrival, flat in between. More arrivals cluster together at higher rates, but the shape is always the same. Random jumps, no memory of when the last one happened. At any fixed time, t, count up how many events happened. Across many simulated paths, that count follows exactly the Poisson distribution with mean lambda t. 2 useful facts. Superposition. Merge 2 independent Poisson processes with rates lambda 1 and lambda 2, and the combined stream is Poisson with rate lambda 1 plus lambda 2. Thinning. Keep each event independently with probability p, and the kept events still form a Poisson process, now with rate p times lambda. The constant rate assumption is the idealization. Real arrival rates often vary with time. That's a non-homogeneous Poisson process, a natural but more complicated extension. The Poisson process. Events arriving independently at a constant rate, with n of t Poisson distributed and exponential gaps between arrivals. Continuous time's answer to independent, memoryless randomness. It underlies queuing theory, reliability engineering, and any model of rare events accumulating over time. Next, random walks, sums of independent steps, and the natural bridge from here to Brownian motion.